Initially, we studied about generation and recombination process and further studied generation rate and recombination rate. After that, we discussed how generation rate is a function of temperature and recombination rate is dependent upon concentration of free electron and hole as well as temperature. After that, we derived a very important and useful formula which is square of intrinsic carrier concentration equal to free electron concentration multiplied by hole concentration, where free electron and hole concentration are meant for an extrinsic semiconductor. This equation is called as mass action law. After that, we discussed about compensated semiconductors, which are extrinsic semiconductor doped with both N-type and P-type impurities. The most basic equations used for solving numericals are: first is the mass action law and the second is charge neutrality equation, which can be written as these two equations are the most basic equations. And after assuming different approximations, we will get different equations for finding the hole and free electron concentration. First approximation is that 100% annihilation has taken place, meaning that ND is equal to 0. Similarly, PA is also 0. So the second equation will modify to substituting the value of hole concentration from the mass action law, we will get a quadratic equation, and after solving we will get the free electron concentration to be equal to now if we assume further that the semiconductor is a normal N-type semiconductor, then Na will be 0, which will modify the above equation for free electron concentration to again if we further assume low level injection, meaning that doping concentration is significantly greater than intrinsic carrier concentration, then in the above equation we can ignore intrinsic carrier concentration in the under root term. Therefore, we will get the free electron concentration to be equal to. So you see that the majority carrier concentration is approximately equal to doping concentration provided the low level injection condition is valid. After that, we discussed that hole is nothing but a vacancy of electron in the valence band, and hole current is actually caused by the movement of several electrons in the valence band, which seems as if a single hole is moving. Further, we discussed that drift velocity is the average velocity with which electrons move in certain direction. And also, we have a formula relating drift velocity with electric field, which is here mu is the mobility of charge carriers. Mu depends upon different scattering mechanism, which further depends upon the temperature. After that, we saw the relation of drift velocity and mobility with electric field and observed that the relationship changes significantly at high values of electric field. The graphs we observed were like this. Then we discussed that we have two types of current density in semiconductors. One is the diffusion current density and the other is drift current density. Diffusion current density is caused due to the difference in concentration of charge carriers at different points within the semiconductor, whereas drift current is caused due to the presence of electric field. There will be a lot of questions based on equilibrium condition, and you should remember that in such cases only the net current will be zero. The same cannot be said for drift current and diffusion current. Also, to make things less complicated, I did not talk about diffusion current density in the lecture in which we studied drift current density. But say we have an energy band diagram like this. Then electric field will be in this direction and drift current will also be in this direction. You should recall that drift current density is in the direction of electric field. But what will be the direction of diffusion current density? You can see that Fermi energy level is a straight line occupying a single energy band. It means that the semiconductor is in equilibrium. But drift current density alone cannot establish equilibrium condition. Therefore, diffusion current is also present whose direction is opposite to the drift current density but have equal magnitude, thereby making net current zero and establishing equilibrium condition. We used this concept for deriving very important relation, that is Einstein relation, according to which diffusion constant of charge carrier divided by mobility is equal to thermal voltage, which is further equal to Boltzmann constant multiplied by temperature in Kelvin divided by charge on a charge carrier. These lectures are very important, quite typical to use, and brings the end of our first unit. For direct band gap semiconductors, we have the recombination rate equation for free electrons like this. Considering low level injection for p-type semiconductor, we have excess electron concentration as where tau n e is the excess minority carrier lifetime for free electrons, which is equal to 1 upon recombination rate constant multiplied by majority carrier concentration, which is the whole concentration. After that, we derived the continuity equation, which can be written as this equation is for holes, and similarly we can write for free electrons also. There are different types of carrier lifetimes. Remember that these two carrier lifetimes are different. After that, we took a special case of continuity equation where current is strictly due to diffusion and derived the equation which relates the carrier concentration with distance like the under root term is referred as diffusion length of holes and is usually represented by LP. After that, we saw that there are few topics which are present in both electronic devices and circuits and electromagnetic theory, like Poisson equation, continuity equation, and Laplace equation. This equation is called as Poisson equation, and by using it we derive the equation of charge density Assuming that the generation rate and recombination rate are comparable to each other and the injected excess hole concentration is significantly large compared to recombination rate and generation rate. The equation which we derived was here rho v at time t is equal to 0 can also be written as q multiplied by excess hole concentration, and Tr is the relaxation time which is defined by permittivity of the semiconductor divided by conductivity. Questions from ambipolar transport equation and Hall effect are not asked in GATE. At least for GATE 2024 it was not in syllabus. But it is important to keep in mind that even though we study diffusion and drift current for holes and electrons separately, but they do not move independently of each other. We developed ambipolar transport equation which was here d dash and mu dash are the effective diffusion constant and mobility of charge carriers which are provided by we also studied how Hall effect is used to determine the type of extrinsic semiconductor by measuring the Hall voltage, and the Hall voltage is equal to magnetic flux intensity multiplied by current flowing inside a semiconductor divided by charge carrier concentration multiplied by magnitude of charge on a single charge carrier multiplied by width of the semiconductor. Charge carrier concentration n multiplied by magnitude of charge on a single carrier is sometimes also written as rho, which is nothing but the charge density. Another term related to Hall effect is Hall coefficient, which is equal to 1 upon charge density. And here our first unit is finished.